Okay, 1 second. I just need to figure it out where we were. I think we were around here. I think. Yes. So, well, welcome to everybody again. Can you hear me? Okay.
Yes.
Great. So I will share with you my screen in a second. Let me know if you see it. Okay. Can you see the screen?
I see you, so I don't know
Okay.
why.
If you see me, that's good, but still not okay. Um, Now it should be okay, yeah?
Yeah, we see the
Good.
presentation.
Good. So uh, we were speaking about the designing for comfort. Just give me 10 seconds. Okay, I need to get my mouse. Okay, so speaking about we were speaking about designing for comfort, and we were looking at the part where we said, okay, let's look at how the Windows could support me to bring some more extra energy into the building, therefore allowing me to have a far better energy balance from this point of view. And we were speaking about the different characteristics of the Windows, among which one very important index, if you wish, is the G value, which it tells you how much heat does the window allow to pass. Yeah? It can be so that if the G value is very high, basically all the energy will pass through the window, therefore you will get a lot of heat through the windows. Or contrary, you have this G value low, then you have a lower heat gains through the windows. In the end, it's a question of putting together several things, because you can play in different ways, and this is up to the imagination of each and every one of you how to do it. You can have a more traditional, if you wish, approach, saying, okay, I have some building that I have to do. I will make sure I have some vegetables, sorry, some trees, some vegetal shading, and if this shading is from trees with falling leaves, then during the winter there are no leaves. The sun will be able to pass through my windows, and therefore I will ensure maximum solar gains. On the other hand, during the summer, if the tree it's green, you have this shading from the tree. Therefore, you will have much lower heat gains, and this is one way in which you say, okay, I can maximize my solar heat gains during um, the winter, and I will minimize them during the summer. Another way to do this uh, is by playing with some shading devices. Well, this can be any kind of shutters that can allow you to reduce this G factor by up to 0.2. Can I make a stop, and I kindly ask you, I'm not seeing, but can I kindly ask you to put on mute, because there is some background noise, if it's possible. Thank you. So I was saying about these shading devices. They can come in different forms. It can be very well, static ones. They can even be part of the design as such. But as well, you can have some ideas here with automatic one. They can be linked with sensors these days. It's nothing extraordinary to link them to the thermal sensors, and this way you can, of course, they get activated, and by getting activated, they will obturate the view, and therefore you will not get overheating inside of a building in a space and so on. The problem with this solution is that, of course, you can do that, but if it is a meeting going on, or you need to study or whatever, it means that you need to renounce to a certain amount of light. So on one hand, yeah, it's not going to get too hot, but on the other hand, you will reduce with a fraction that can be higher or lower the amount of light that will penetrate the room. Then you have the other possibility, or third possibility, fourth possibility, if you want, in which you can have some kind of horizontal shadings, and depending, of course, again on the position of the sun during the winter. When the sun is lower, the sun will be able to penetrate through the window, while during the summer, if it's up, then you will have shadow, and as such avoid overheating. There are several ways that you can do that, and of course it's a question of putting them together in the same design. I wouldn't say that it's one solution fits all, but it's rather playing with different solutions. So either shadings, either automatic ones, trees, or vegetation, or you can just pure and simple play with the glazing itself by selecting the right G value according to the needs that you have at that specific point. And then I made some simulation just to give you an idea of what it means in terms of playing with the sun. You can see here I took into account, for a standard house, I took into account low E glazing with a new value of 0.5. So this is a good window in terms of thermal insulation, and with a G around 0.5, so just in the middle. And then by looking and making some analysis for different climate zones. So you have a climatic zone where you take into account during winter -12, -15, -18, -21, -25. So again, Northern Europe, I would say. You can see here the heating demand, you can see the cooling demand, and you can see also the frequency of overheating. Basically, the percentage of time when during summer you will have temperature which are above 25 degrees. Yeah? So this is just to give you an idea about it. It's very good from heating demand point of view. It's quite low if you look at. Just let me get my pointer. If I'm looking at the standard climatic zone, let's call it this way, where you have a -12 Celsius centigrade for calculation during winter, or even a -15. In case of good insulation, you have a heating energy demand lower than 15. But then also you have some frequency of overheating, which is important. You need to take this into account. And I did the same play, same analyze, if you wish, with this time with slightly higher glazing solution. So this is by 20% less performant. Yeah, and instead of 0.50, this one is 0.60. However, I used a glazing with about 30% lower G value. Basically, this meaning that I will have a lower amount of heat which will come through the window into the house during the winter. And well, you can see here the decrease of the frequency of overheating. There is a increase in the heating demand, but on the other hand, there is also a decrease in the cooling demand. Yeah. So from 13 to 14, I'm decreasing to 10, 11, while for heating, I'm increasing from 7, 6, 7 up to 11, 12. Again, this is the kind of well, simulation maybe for large buildings. I would say it's important to look at it. But just to give you a feeling that you can look also from this perspective, sorry for that. You can look also from this perspective at the window, and there are sufficient softwares available that you can simulate that. You can always in your professional activity get in contact with somebody who is, let's say, maybe dedicated specific to this part of energy efficiency calculation, like an energy efficient auditor or something like that. And this kind of simulations, they can be done, and they can give you from as early as a sketch, if you wish, an idea of, okay, do I go into the right direction, or well, maybe I need to make some adjustments at the moment of the design of the envelope. Okay. Okay. Then another important point in all this this equation, thing which is becomes of even more importance once you increase the amount of efficiency of the building, once the buildings are even better insulated than now. It's the avoidance of minimizing the thermal bridges. Yeah, the thermal bridges are basically those junctions, those parts of the building where, for different reasons, it can be because of the geometrical form, you have higher losses of energy, and this you can find it pretty much everywhere. You can find it in the foundation slab, you can find it in the ceiling or in the basement ceiling, at the balconies and so on. Balconies are really a very good example. I don't know if I have it here. I will just show it to you briefly afterwards. All these parts where the building, because of various reasons, is no longer insulated as good as the rest of it, you have to take a look at it. This can be summarized. And if in the standard design, let's say, we do not, the tendency was to overlook them. Now, when you need to go to very low consumption, this needs to be treated with fairly more attention from your side. It's a question of doing some correct details, and you have here some examples. For example, this here you have an external wall connection, and here you have a little bit of a thermal bridge, yeah? Because both this part and this part here, they are not very well in terms of thermal insulation. So one way to solve this is, for example, by adding here a material which in terms of thermal insulation is better than the concrete that you have there. Yeah? The other way, or the same principle, you can apply it here. You can see it pretty much the same thing. These thermal bridges, they are calculated normally by a thermal auditor, but it's also something that can be supported from the design. Also here, and I will maybe spend a few moments on this one and on the balcony, and just allow me to make a short short introduction here. 10 seconds it will take. Okay, so I was saying this is the way that you should look at the window, and then to speak a little bit about balcony. But before that, if we look at the way that you can have a window, imagine that this is your wall, your existing wall. Please excuse my designing, my drawing. I do it with the mouse. Now, if I do this, normally or usually you put the windows here, and then this is the traditional way. And then from here you can go to the next variant, which is in the same approach. I have an existing building. Okay, this is my wall. I have here my windows, and then they decide, okay, let's do some insulation, and they decide to put some kind of insulation here, let's say 10 centimeters of insulation, and they put also 10 centimeters of insulation here. And sometimes this is all they do, and in some other cases they will put also some insulation here, like this, more or less. Yeah? Now, the reason for putting this insulation here is very simple, just to avoid the thermal bridges. Yeah? But still, as you can see also from the drawing, most of the time you do not have sufficient thickness here to put the same amount of insulation like you put like we put on the standard wall. You will put maybe 2 centimeters. Then this is a thermal bridge, and it can generate also some issues with some condensation if it's not sufficient. And then you have here a detail on how you can make this detail. You can see it here. Basically, the insulation is covering the frame of the windows, which is already insulated, and this way you ensure that there is no thermal bridge in the area of the windows. If you remember the first image, the thermal scan that I was showing to you, in case of windows you can always find this if the detail is not solved correctly. So this is one point where looking a little bit at the details can make a difference, and can let can give the design a value of, okay, I've been thinking about how can I solve this. And then there is another way, or a very common design, in which if you have a multi-story building, then you have the balconies. something like this. Sorry, come on. Okay, and of course the balconies are part of the floor slab. Yeah, and if you try to I'm speaking now about a hypothetical example of a renovation. You can try to insulate this part, you can insulate this part, but most of the time this one is not insulated as such. And basically this is a huge thermal bridge. Yeah? Now if I start doing from the beginning this, I would need to insulate all the way just to make sure that I'm continuing the same principle. But this is neither economic, it's not easy feasible, and it's not for sure not looking nice. So instead of that, I can have here a desolidarization, if you wish, of the structure. Either I can think from the beginning and the two structures, the living or the building itself, it's one structure, and the balconies, the structure of the balcony is separate from the building, therefore not having contact and not existing thermal bridges. Or if not, there are existing plenty of solution with fixation with thermal bridge breakers.
Gabriel, there is
Yes,
one
please.
question, probably similar what you mentioned right now. The question is, what is your opinion? Will it change the situation if the profile itself have thermal cut? That means probably about the windows.
Yes. So I think I just lost the yeah. I will just read you it very fast. Basically, this is one answer. Yeah, within the fixation, and of course this is a question of static as well, but you can have some kind of thermal braking within the system. And at this point, it's a question of thinking about it, not calculating it. For the purpose of the contest, you don't have to calculate this. But taking this into account and thinking about it means you already give an answer. Of course, if this is the balcony and somehow it's a loggia is no longer a balcony, which means that you close it. Yeah, you close it at each level, and then you just insulate here, and here you have glazings. Then there is no discussion about thermal bridges. But again, it's just an example to rise your mind to say, okay, think about also about this, because these are issues which appears, and these are issues with which you will deal in the future in terms of design. I don't know if I are any more questions here.
No, there is just one. There was just one.
Okay. Well, just to come to add something on the comment from Professor Agno, it will depend a lot of time also on the static. We see this a lot in, at least in Romania, we see it a lot from static point of view because we are in the region of earthquakes. So the desolarization of the balconies is a very tricky question in terms of this in Romania. In some other countries can be made. It's made, I think, fairly often in Germany. So it depends from case to case. Here is just to give you some hints and some ideas about it. Okay. So let me go further. Okay. Now, if we spoke about the designing of the envelope, then it's a question of how you how you take into account the orientation. Yeah, of course you can design it for according to your will. You need to think into account that on one hand, if you need more solar gains, then you would, if you are free from the design, you can orient it to the south. This it's also a question of how do you see it from other visual constraints of the seat itself, but also you need to think about the envelope itself, and the envelope itself. Well, a complicated design, yeah, will increase the energy demand compared to a very straight, compact building style. But most of the time here there is a slight misunderstanding. It doesn't mean that you cannot have a compact design and the shape which is not that compact if you think in terms of heated envelope. Because if I take this this image here and I consider this part from the design as out of the heated envelope, and my heated envelope basically ends here, then my design, although it looks more fragmented, it's still compact. This is very important to think about it and to understand it, because there is a very direct ratio or impact on the building itself and the consumption that it has, and how do you look at this this consumption per square meter. Yeah? If I take into account, I have here two calculations, variant 1 and variant 2. In the case of both of them, the footprint is basically the same. It's 200 square meters, but on the first one I have it only on one floor, and on the other hand, on the other one I have it on 2 floors. While in the case of the first one, the surface of the envelope, it's almost 600 square meters. It's about 25% lower in the case of the second one, and that's why this this idea of minimizing the envelope area aspect, the report between the area and the volume should be lower. That means that basically within the same volume I'm accommodating a higher area. Therefore, although the overall consumption it's pretty much the same, the consumption per square meter, and if you think in square meters you can think in families, it's lower. So you can see the more compact you go from this point of view, the easier would be to achieve the energy efficiency requirements. But still, bear in mind that the energy requirements, they refer to the heated envelope. So if you have we were speaking about balconies, if you have some balconies which are outside the heated envelope and which are as well thermally bridge or with thermal bridge breakers, then that part it's not taken into account in the calculations. You have a building which looks close to your heart or close to whatever you're thinking in terms of design, while still accommodating a very good energy efficiency. It's not one thing will not allow the reach of the other one. It doesn't mean that if I need to make an energy efficient building, the building will be ugly. Sometimes you feel this, or you can see some comments like that. No, it's just a question of how do I look at the design from the early stages and make sure that whatever I treat with the good tools, so that I can give the expected design while achieving also the technical criteria, if you wish. Then I think I have one more example here, pretty much within the same area. Of course, these are the way that you lose energy because of the geometric forms. But if the geometric forms different, like from a ground level to a 2-story height, then the percentages as well will be different. So if in the case of a single family house like this one, I don't know, I have well, here it's 43% of the surface, it's represented by the roof. In a case with of a construction with 2 stories with the same surface, the roof will be only 26%, while the external walls will be 48%. And this has also importance from how you treat the thermal point, from thermal point of view, the different designs. Yeah, if I have a higher amount of external walls, then I will be sure that I treat it very well, the walls, if these are within the economics of the building, the highest surface. Okay, now this was more or less about the envelope, and now we are going a little bit we continue with few words about the airtightness, and I have here a very short movie that I would like to share with you before going into it. But maybe just to give a little bit of time to see if we have any more questions. No questions? Okay. You can still hear me, yes?
Yes, we can hear you.
Okay. Thank you, Karel.
Yes. Yes.
Yes.
Okay, so just to share with you a movie about, this is a movie about air tightness and how do we measure air tightness. Is in German, I think. I beg you forgiveness for that. I didn't find it, the version I had it
Shortly
in.
before finalizing
Oh, no,
the construction work, it must be ensured that the whole structure is completely airtight, a delicate but highly important.
Can you hear it?
This final airtightness check is one of the most important.
Yes, we can hear it.
Ensuring the energy efficiency of the building envelope, as well as the thermal comfort of the residents. The airtightness measurements are carried out at different air pressures to ensure an adequate level of precision and to simulate real conditions as authentically as possible. After windows and doors have been closed, all pipes and ventilation shafts are covered with elastic orange balls. A fan draws the air out of the building until a pressure difference of 50 pascals is generated between the inside and the outside of the building. After that, the flow rate needed to maintain this pressure difference is determined. 50 pascals simulates the pressure on the construction and corresponds to a wind velocity of 30 kilometers an hour. A computer controls the speed of the motor that is used to vary the pressure applied to the house in its entirety. The pressure has to be applied in both directions, in and out, causing overpressure on the one hand and underpressure on the other hand. The technician may change the quantity of air exchanged by using various cylinders on the blower. The building envelope could be compared to an elastic membrane reacting to pressure differences. The computer measures and displays the different response times. A series of air exchange values is recorded, which correspond exactly to the volume of air escaping from the building. The relation between the air exchange established at a pressure difference of 50 pascals and the volume of a room provides the N50 index. This value represents the percentage of total renewals of the room's air volume in 1 hour at a pressure difference of 50 pascals. Experience has shown that it's useful to combine the blower door test with IR thermography, as this is a method of making leaks directly visible. At this stage of the construction work, the Vario membrane is still accessible. Therefore, small corrections with the Vario tape are possible. For an Isover multi-comfort house or a passive house, the value measured by the blower door test should not exceed an air exchange rate of 0.6 per hour. In our case, the result is 0.46. This proves that the planning of the details and the construction work were properly done. With new lightweight buildings or renovation projects, this test is done before the cladding is fixed, so that any weak spots can still be eliminated. With solid structures made of brick, concrete and stone, however, the test is done after the building has been rendered. The blower door test for measuring a building's airtightness is one of the standard methods included in the quality control program for energy efficient houses, especially multi-comfort houses and passive houses. In addition, the planning and building authorities in some European countries now demand a certificate of airtightness for buildings, which is part of a drive to increase the quality and workmanship.
So, just to introduce the air tightness, and well, this air tightness, it's a part of the criteria that we have to meet within the task. Basically, this air tightness has links with four other topics. It gives you an idea about the energy efficiency. It gives you an idea about the thermal comfort. It will support the protecting the building fabrics, and last but not least, it's linked with also with the health. And as already mentioned in the movie, and you have it also in the task, this is a prerequisite for many of the countries' energy efficiency regulation, which means that basically all the buildings in the future will have to be airtight. By having a building airtight, it doesn't mean that I'm not going to be able to breathe in that building, because I will need to find other ways to provide the required air. But it means that I will not lose energy basically through the cracks, through the gaps, and I will ensure that the quality of the job is properly done. There is a link between the different levels of air tightness and the heat losses that you have. And if I look at this graph, which is showing you the estimated losses per in kilowatt hour per square meter and year, you can see here that if the buildings are really poorly designed or not airtight, the amount of energy that you lose through the cracks, through the gaps within the construction, it's already higher than what we need to obtain as consumption. Yeah, the consumption that we need to be for the task is below 15 kilowatt hour per square meter in year. So in the objective of the task, I believe the level it was set to be below 1.5, and it can be even lower. You can obtain these days very tight buildings, which basically mean that the building was constructed correctly, that when two walls are put it together in case of prefabricated systems, there is no gap, so I will not going to have some drafts in the area. I will not have any pollutants coming inside my construction from outside. And this is a very, very good way of checking the quality of the construction itself. It helps within the designing, it helps within the construction stage, and it can be done in several steps. And I think majority of the European states have this airtightness measurements in the thermal regulation. And as was saying in the movie, that means that within 1 hour, at a difference of 50 pascals, my building with exchange with the exterior, if I have it at 1.5, 1.5 times the volume of the building. So it's still not completely airtight. You can imagine how is the situation today when we are exchanging around 4 or 5. It's reduced, and by doing so, it's like closing the windows. I don't have a construction which is very well insulated, and then I keep the windows open, because then I lose all the job that I did before. Airtightness. Then the second step of the airtightness is the fact that, as I was mentioning, this has to do also with the quality of the air inside. If I'm bringing the air inside through a ventilation system, then I can say that, okay, I'm going to use some kind of filter for particles, for pollen and so on, and I will remove already a lot of the harmful things which are in mostly in the cities, in the area. If my building it's very leaky, if you wish, then the same amount of pollutants that I have in the outside area, it will be all as well inside. So from this point of view, ensuring the right amount of airtightness, it's critical also for the quality of the air. Just imagine having a house or construction, an office, which is by an autobahn or by a very trafficated route where you have a lot of benzene and so on, and this construction, it's extremely leakage, or it's very open from this point of view, and you get all these substances inside the air. This is not at all good for your health and for the inhabitants as well. That would be a second point. And then if you look further and we think about construction which are made in wood, the air tightness is very important as well to avoid damaging the construction itself, the structural integrity of the construction, because by not ensuring the air tightness, it means that all the water vapors that I will generate inside through all the activities which are common in a building, due to the pressure difference, they will try to migrate in the winter outside. So they will try to find their way outside. And at a certain point, because of the difference of temperature, let's assume that here you have, I don't know, 21 degrees, and let's assume that outside you have -15. Okay, at a certain point they will find the right condition to condensate, and when they condensate, you can get all kind of issues like this, from mold flow, from mushroom, and all kind of things like that, up to the way that because of long exposure, the structure itself has been deteriorated. Therefore, it's very important to have this airtightness established, very well done, checked, properly checked. And this way you can ensure that a building which is very energy efficient, very well insulated, will stay proper. Then, just to give you an idea of what it means, well, in case of a construction which is about 100 square meters, if I need to be somewhere around N50 equal 3, the sum of all cracks and gaps and everything else within the envelope would be around half of a A4 paper, just to have an idea. So basically, if you wish, equal to a window from the bathroom. Yeah, that's to give you an feeling of how it goes. Then this airtightness, it's easy to treat. You can, as you saw very well, visualize it with the support of some thermographics camera and with the blower door test. This blower door test is today something that it's very common and as mentioned in many countries. And once you have placed it from the design stage, when you are at the construction stage, just before covering the airtight layer, you can do these measurements. You can see eventually if there are any penetrations, if there are any things that have to be resealed. And then by using different methods, you can ensure the level that you required is obtained. And as such, provide all the things that we were speaking, starting with reducing the energy losses, but continuing with the quality of the air and integrity of the building. Different type of building elements that can contribute to the airtightness. The airtightness can be obtained with using the concrete structure of the building itself. You can use, in case you have some kind of wooden constructions or wooden parts, foils, you can use plasterings or pure and simple the windows. These days they are far better than the ones used many years ago, including the frame itself, basically providing an airtight layer to the building. So the airtightness layer should be continuous as much as possible, and well, if you are able to draw it without taking your pen from the papers, it means that you thought very well about it and you solve it from this point of view correctly. Right. Here one construction detail is the junction between a wall and a roof, and you can see here the position of the airtight. This is something that would be, I advise you to look at it and to think about it in your details, to think about where I should put my airtight layer so that I ensure the integrity of the building. Sorry. The integrity of the building from this point of view. And then, last but not last but not least, a few words about ventilation here, and then a little bit more in the indoor air quality. If I'm ensuring that my envelope is tight, then for sure I need to bring some air inside, so that I can breathe and I can live properly. And one way to do that, it's through natural ventilation. But natural ventilation, it means that you have a lot of uncertainty about the quantity of air that you get inside, and I'll show you some graphs. And also, you are not able to control the heat that you lost. Basically, you have heated your air inside, and then you say, now, okay, I need to bring some fresh air. I take all this heated air, I throw it through the window, and then I bring in inside the room some air to breathe, but which is still cold, like it's outside. And then I need to reheat this one. And by reheating, what you do is basically you throw the energy through the window. It's like heating outside, if you want. So another way to do this is to look at and to think about having a controlled ventilation. This controlled ventilation can serve several purposes. First, the purpose would be to provide the inhabitants with the amount of air that they need to breathe at a good level. But also, if you look at it and you think, and there are plenty of solutions today on the market with heat exchangers, basically you could design and think together with an installation engineer, or in your future design, you can think about using all the energy that you heated the air somehow to recuperate it and to use it to also heat further the air which is coming from outside. It's pretty much like the principle of a radiator. You can see it here from a very basic sketch. I have the outside air, which is cold, okay? I can always use some kind of earth heat exchanger to preheat the air. And then once it comes here in the heat exchanger, it will meet the exhaust air that I take from the house. And within this heat exchanger, the transfer of heat between the two will happen. And as a result, I will be able to get a big part of the energy from the air that I'm taking out, the vitiated air from the house, preheat the air from outside, and bring inside fresh air at the room temperature with only a fraction of the energy. This is a standard technology existing, and it's very well used. And again, you will find it in many European countries as a prerequisite in the nearly zero energy building regulations. And just few examples here without going too much into the details, because you have also a part of renovation in the building. Here you can see a building, a residential building of 2 stories from Mannheim, which was renovated before the construction, somewhere around an estimated 300 and what? Sorry. 320 kilowatt hour per square meter in year, and then after the renovation around reach a level of about 11 kilowatt hour per square meter in year, with very good levels of daylight autonomy, averaging from 55% to 65%, and air tightness under 50 pascals at 0.6. So just to show you, this building was able to reduce the energy demand by 95 degrees. Sorry.
Gabriel, you're muted.
We can hear you, Gabriel.
Okay, when did you, can you hear me now?
Yes,
It's
yes,
okay
we
now.
can hear you.
Okay, when did you lost me?
Two slides ago.
Okay, here, this part?
Yeah.
Okay, thank you.
Yeah,
Thank you. So I was saying that, well, if I repeat myself, please excuse me. I was saying that this was a renovation done a few years ago in Germany, in Mannheim. It's a residential building which was renovated for two purposes, for residential and for offices as well. The estimated consumption before the renovation was somewhere around 320 kilowatts hour per square meter and year, and after was 11 kilowatts, so pretty good reduction of it. Also, you can see here some information about the daylight autonomy in the office and the average daylight autonomy also in the residential area. And then also very good results in terms of air tightness and overheating. So I just selected some of these details just to show you how it was done and to give to the competitors an idea of what they can do. Roof insulation above and below rafters, the attics for the external walls and the ceiling above basement. You can see here an image of the construction. So this is the existing construction itself, and then, first of all, the insulation, you can see here one layer and then another layer here. All together, I think it's 20 with some kind of 14, so roughly about 30-35 centimeters of insulation. Also, very important, the airtight layer, which is placed somewhere here. You can see it in the detail. And that's allowing the construction to achieve a U value of about 0.11 in line with what we would need also to obtain in the task. But again, this is just as an idea. And then you see you can see the same principle for the external walls. You have a wall of about 20 centimeters of brick, and to this 20 centimeter of brick here, two layers, one layer, second layer of attics has been added closely to 26 centimeters of 25 centimeters of mineral wool as external insulation. Making it or allowing the construction to reach a U value of 0.12. And I think I have one more detail, yeah. This is a detail from the floor above the basement. Again, the construction with a 20 centimeter concrete floor, and you can see it has added layer above and a layer of insulation below. And in this case, you can see here also, in order to reduce the thermal bridges that were coming from the foundation looking a little bit like this. So there was insulation here added. They added insulation here and another layer here, just to minimize as well the thermal bridges of the construction, and again keeping the thermal requirement within the same area. So designing for the thermal comfort, just you know, in a nutshell. Thermal insulation, air tightness, good windows and doors, we talked about them, solar gain, internal gain, and ventilation system with heat recuperation. That would be, yeah, that would be the main points that you would need to look at your design when looking at the thermal comfort from this perspective. And before going to a short intermezzo with questions and some discussions, just to give you an idea, here you can find on the website of the competition. I recommend you to take a look at them. Also some food for thoughts, if you wish. There are several pilot projects from the colleagues in Poland. One, it's a new construction in Warsaw, as you can see it. The other ones, one in Gdansk, and I will avoid naming the third one because I'm not sure about my pronunciation. And by looking at it, you can find, I would say, ideas on how they manage to work with it. You can see that from this perspective, you have, well, I would say more of a cubic approach, if you wish, with integrated. We were speaking with integrated sun shades within the windows. You have more of a traditional approach here with some ethics lights and roof windows. And here you can see also some ideas of how to integrate the PV on the roof and how this could support you within the design. So I recommend you take a look at this. This is not only from Poland, but you can find also some ideas about other construction, and that could help you to think in terms of how to design. That would be from view. Let me just go to this and catch my breath by asking any questions. I'm sure, I hope you heard me this time, so. Can you hear me?
Yes, we can hear you, but probably no question.
Okay. Well, if there are no questions, by the way, help me ask some questions, because it's always good to have an interaction and to make sure that the people are on the same line with you.
Okay, so maybe there is already one. What is your opinion, or you can also see it? Okay, so
Yeah,
what is your
Karim.
opinion about the use of photovoltaic? Does it affect the building system?
Well, Fernando, I'm not sure what do you mean by affecting the building system. You can integrate in your design photovoltaics. You can integrate in your design any kind of active measures that will allow you to generate green energy. And there are so many of them. You can use heat exchangers or Canadian well. You can use solar collectors and so on. By integrating the photovoltaic, the PV in your design, I don't see why would you affect the building system. It's just a question of, on one hand, ensuring that you decrease your needs for energy. On the other hand, making sure that the photovoltaics are integrated in the general electricity grid, and when you use it, you can take it. You can take the energy, and if not, most of the time this is what happened. The electricity which is produced and is not used is given to the public grid of electricity. There are some discussion if the grid as such has been developed or can sustain if all the houses will become energy producers. But I think it's a little bit too early to have some conclusion on this one. So if you ask me, yeah, make sure that you integrated it, but keep in mind that if you take a building and you build it with very low level of energy efficiency, you can put photovoltaic on all of it. It doesn't mean that you make it green. I'm pretty sure you will not be able to cover all the electricity need that you have in that house.
There is other question, Gabriel. Which aspect do you think remain unexplored within the building envelope that might affect the building ability to perform optimally thermally?
Well, I think that if you look at, I mean, this is not rocket science. This is something very well established. If you look at the envelope, if you look at the way that you organize and orient your building by ensuring that on one hand, with the treatment of the envelope, you decrease as much as possible the losses. And by taking the right measures to orient the building, on one hand, you respond to gaining the energy that you need without affecting, on the other hand, the comfort during the summer. This is pretty much covering this part. So this would allow you to have a balance energy balance. Also, but it's not sufficient. You need to think about in terms of airtightness, and this is more at the design stage of thinking about an airtight layer. You cannot measure it on the drawings. It will be measured, this is measured on the construction site. And then once you ensure this, for all the reasons that we were discussing, you also need to think about bringing air inside. Without air, you cannot live. So you need to ensure that you bring air. And it's either you use natural ventilation, you can think about it, and in some cases there are designers that prefer natural ventilation, then this is an answer. If you are in the middle of a natural place where you have really good quality of air, you can think about maybe using natural and mechanical. Me, I'm more into a favor of having a controlled one, because if it is in a city, these days the cities are not the places where you have the cleanest air in the world. And as you will see, and we'll discuss slightly also tomorrow, you need to ventilate also during during the night. So I'm not sure that somebody will open up the windows all the night, or if you leave it open, then as I was mentioning in the morning discussions, you can always wake up with the tram. So yeah, it's a choice, I would say. If you look at this, then the building should perform thermally optimal. Of course, on the long run, there is always the question, what if the functionality of the building will change? But this can be also taken into account from the design stage. You can think about, okay, maybe here in the future could be some offices, and then look about it. But I think we go a little bit too far at the stage of our project right now. Sorry, I hope I answered to your question, Tuto. Sorry. Okay. Now, well, yeah, few words about indoor air quality. Please let me know if you can still see my presentation.
Yes, we see it.
Okay, super. So, before going to a short video, just to have a recap, I think this is very important for you to remember, and this is something that you can often find if you make measurements, even in places where allegedly the quality of air should be very good, like in universities, for example, because this I think it summarizes very well the quality of the indoor air. If you have very poor quality of air, and if because of various reasons, and you will see, you go to very high concentration of CO2, then the performance of the human body decreases. This is nothing that we can do about it. This is the way that the human body functions. And if outside you would have around maybe 400 parts per million CO2 concentration, a good but seldom found concentration would be about 600. You can see, okay, 1000 is still a good level, but in many situations you have very high levels of CO2. And this has an effect on human performance, from learning to feeling dizziness and not being able to make the right decision. So before going to more discussion, let me just switch to this presentation, which speaks a little bit about
vital. We can live 30
Can you hear it?
days without eating, 3 days
Yes,
without
yes.
drinking, but only 3 minutes without breathing. Throughout the ages, air quality in buildings has been recognized as a source of well-being and essential to good health. For instance, in preventing the spread of diseases. The quality of air has dramatically changed over the last couple of centuries. As pollution levels have risen, attention has been given to the threats of outdoor air pollution on human health and the environment. It is only in the last few decades that attention has been paid to indoor air quality. The sources of indoor pollution can be divided into 4 categories. 1. Outdoor sources. 2. Occupant-related activities and products. 3. Building materials and furnishings. 4. Poorly maintained ventilation systems. Insufficient concentration, pollutants can have a direct effect on health. Their effects on our well-being can be less easily quantifiable. Odours originate from various sources. They are generated by volatile molecules that the human nose can detect at very low levels of concentration. Some volatile molecules can also cause sensory irritations. Generally, the threshold for sensory irritation is higher than for odour perception. The sensation of stuffiness results from the overall pollution load and lack of fresh air. Different pollutants at very low concentrations, but combined, can affect our well-being. Good air quality is defined by the absence of health-threatening pollutants, bad smells, sensory irritations, and stuffiness. The physiological aspect of indoor air quality. We inhale and exhale an average of 12,000 litres of air per day. Our ability to assess the quality of this air involves 2 senses. 1. Olfaction. The olfactory nerve in the nose detects molecules. The information is sent to be interpreted as a smell in several parts of the brain. The cortex, where conscious perception is formed, and the limbic system, which controls mood and emotions. 2. The common chemical sense. This is the ability to sense irritants. The process is fairly similar, but involves different nerves. The physical aspect of indoor air quality. Air is a gas, mainly composed of oxygen, 21%, and nitrogen, 78%. The remaining 1% can concentrate a number of pollutants. The different indoor pollutants can be classified into 2 main categories. 1. Physico-chemical pollutants. 2. Biological pollutants. Exposure to pollutants is influenced by environmental parameters such as ventilation rate, air velocity, temperature, relative humidity, the activities taking place, and the frequency and duration of exposure. The socio-psychological aspect of indoor air quality. The quality of air has a profound effect on our conscious and subconscious mind. Odours are deeply linked to our emotional state, motivation and memory. If unpleasant, they can cause mental distraction and have a negative impact on mood and stress levels. The presence of pollutants in buildings is shown to decrease efficiency. For instance, high concentration of CO2 impairs our ability to take decisions. This is why we are usually more creative, alert and efficient in well-ventilated schools or offices. Designing for indoor air quality. To improve indoor air quality, 3 factors have to be considered. 1. Removing or minimizing emissions of pollutants at source. However, it is not always economic, practical, or even possible. 2. Ventilating. The appropriate extraction and replacement of air depends on levels of occupancy, activity, etc. 3. Purifying the air by filtering incoming air and indoor air. However, these filters need to be maintained to prevent the ventilation system itself from becoming a source of pollution. Mechanical ventilation can be very efficient when used appropriately. But we should not forget the benefits of natural ventilation, particularly in terms of health and cost. User control and contact with the outside world are key to making us feel comfortable. However, the benefits of natural ventilation depend on what this outside world consists of. Ventilation can be a source of noise or thermal discomfort. A balance is to be found to reach the optimum solution. An idea gaining ground is for hybrid ventilation, natural ventilation in mid-season and mechanical in winter and summer. The future. Our indoor air quality needs will probably remain the same. However, our understanding of indoor chemistry will surely evolve, allowing us to better detect and interpret the thousands of indoor air pollutants. In order to improve energy efficiency, the use of mechanical ventilation systems is likely to change. New means of renewing air efficiently while maintaining a comfortable thermal environment will have to be developed.
Yeah. Can you hear it? It was okay? You could hear it, yes?
Yes, yes, it was okay.
Good. So, well, as was also stated in the movie, there is always a question of ventilating the space. You can do it naturally, you can do it mechanically, you can do it hybrid if you want, but there is always a question of ventilation. So I just want to share with you some measurements that I did when speaking about the indoor air quality. For example, just to give you here is an example of a meeting room, which although a ventilation system was installed, the ventilation system was not designed properly, meaning that it did not took into account the amount of people that were entering in that meeting. So although you can see here the norms, and you can see here the ideal curve, although the meeting started, I would say, in good level. We are looking at the curve in red. Very abruptly, in less than few hours, half an hour, if I remember, I see here in the graph, the CO2 level increased, and despite the ventilation, and they somehow equilibrated themselves at a very high level. So this is roughly 2,400, 2,400 parts per million CO2, and then we can see here a drop, so probably some kind of a break. But you can see that although it decreased, it did not reach the level from the start. Yeah. So probably if it was used, but in a second reunion or meeting or whatever, this space would go even higher. Yeah? This is a measurements from office, and then you can see here some measurements done in some apartments, because we are speaking about residential spaces also in the task. These are 5 days measurements in an apartment where in one room, for example, where there was a small child and the mother, and well, again, here it would be the let's say an optimum curve of about 800 parts per million, and you can see here actually how the curve is going up. Okay, then there is some kind of natural ventilation. Okay, it goes down, but again it goes up. Yeah, you ventilate, when you naturally ventilate, it goes up, but then it goes really fast higher again. And this, in this case, I think it's not a very efficient way of looking at it, because you cannot do it all the time. And if it's really cold outside, and you have some small child as well, then people are more reluctant to keep the window open at all times, especially mainly during winter time when it's really cold. And again, the same here. It's a more complex measurement of 10 days. Done again in an apartment, in one room, where you have only one person, and then a second room, again slightly smaller, and a third typology of room with two persons living there. Again, you can see that during the night, these peaks, they are achieved, basically meaning that you sleep in very poor quality, of indoor air. So this natural ventilation has its limits. It can be used if there are not extreme of temperature, if the temperature is not too high or not too low. But in the rest, when the temperature is really exceeding by far the optimal, the comfort area, then it can be very tricky. Then just few ideas about designing for indoor air quality. Okay, we spoke about moisture management, about mold prevention, and I'm just looking at the design stage right now. Then you need to think about ventilation, and this is most of the time done together with the mechanical engineer. And then you should think about the way that you select your materials. Should be materials that are low emitting harmful substances, or that are checked that do not emit harmful substances or volatile or organic compounds. You can always think about substances that absorb this kind of materials that absorb this kind of substances. Then within the construction stage, okay, this has to be done. The installation has to be properly done, and it has to be cleared and tested. And then also was mentioning, during the operation of the building, it has to be very well maintained. The system, the ventilation system, should be checked, so that you make sure that in the end it's working properly. And well, just two ideas. You can look in terms of products or materials that you can use. There are labels which inform you about the amount of emissions. Or suggest you use products, or you look for products which are labeled as A category. Then we were earlier mentioning about this technology which is developed by Saint-Gobain, which is called Active Air. On top of not emitting, it also helps you absorbing all these substances from the environment of the building. And then, yes, well, think about in terms of ventilation to supply with amount of fresh air. It can be around 30 cubic meters, 25, 30, 35 cubic meters of fresh air per person, and this is this is something standard. I mean, you can find it in most of the regulation to ensure that you have this space very well ventilated. The design, it's rather simple, so this is not something extraordinary. You can always think about having a heat exchanger, mechanical ventilation system with heat recuperation that will decrease also the amount of energy that you need to use for heating. One big advantage of the ventilation system within those areas where the quality of the air outside is poor is the fact that you can always add some filters, and these are good because you can clear up the air a little bit before it comes inside the building envelope. On the other hand, well, you can it exists also some all kind of solution systems and so on. This is from a document from the colleagues in UK, so you can see it's very compact, yeah? And it will occupy small places. Depends on the specification of the system. Then you need also to take into account that this ventilation system will generate some noise, and we'll speak tomorrow about it. If I take care of the thermal comfort, I ensure that the building is very comfortable, that I do not lose energy. Then I take care of the ventilation system. I'm sure that I provided the right amount of ventilation inside, and I have fresh air, and I have it cleaned, and I have it at the same temperature as the environment, so that I do not create any discomfort. Then, last but not least, I should ensure myself that this system does not produce too much noise, so that the users will stop it. And this we will discuss a little bit more in the acoustic discussion from tomorrow. Well, yeah, I just finished with this slide with the interaction. As I was just mentioning, you can see if I checked the thermal comfort and I have to check the quality of air, they work together, and the amount of air tightness and the amount of ventilation will influence both of them. Yeah? And then we will see tomorrow the link with the acoustics, and we'll look a little bit further at the link with the visual comfort. Thank you for your time. If you have any questions.
Thank you. Thank you, Gabriel. I would have one question.
Please.
I'm sure my students are very interested in when, this is a general question, when these recordings are on competition website, have you any?
When they will be on the competition website?
Yeah, when?
Well, I have to ask Eric, but I suppose they will be immediately posted, like in a matter of days, maybe 1 day, 2 days, something like that. As you know, these are most of the time done very fast, and I assume after after tomorrow we will put it online, but I have to ask Eric when it will be updated.
Okay, yes, thank you.
With pleasure. Well, guys, if there are no more questions, I would thank you for your time, and for your patience. I hope I didn't abuse it. And see you tomorrow to discuss about a little bit about acoustics and a little bit about visual comfort. Meanwhile, if you have questions, do not hesitate to ask your contest coordinators inside Saint-Gobain and to ask for their support and for their guidance with questions, because the library and the documentations which are available from Saint-Gobain, they are pretty extensive, and I encourage all of you to check it. Thank you for your time, and I'll see you tomorrow.
Thank you. Bye.
Thank you.
Bye bye,
See
guys.
you tomorrow.
Bye-bye.
Ciao. Bye.